this section, we are going to learn about the vertex form of a quadratic function. Just like we have a standard form of a quadratic function, similarly, we can represent a quadratic function in the vertex form. So to understand the vertex form, first of all, we'll have to understand what is the translation. We'll discuss two types of translations right now, horizontal translation and the vertical translation. Horizontal translation takes place when we add or subtract something to the input of the function. Let's say we have a function y equals fx, and we are going to add or subtract something to its input value. Let's say we're going to add or subtract h this time. So we assume a parent quadratic function, which is y equals x squared, and we now try to add or subtract something to its input. Suppose it's x plus 3. We added something to its input, so we change the input value only, and okay, it's whole squared. So the original graph of the y equals x squared looks like this. When we add something to the function, when we add something to the input actually, the graph shifted towards the left direction by the same amount. So 3, so now it got shifted towards left direction, and it took 3 units to shift it here. Similarly, let's say I had the same function y equals x squared, and this time I'm going to subtract something here. Say this is x, and I'm going to subtract 3 this time here. So this time what happens, and let's say we have my original function like this. So my graph will be shifted towards the right direction by the same units. So now it goes towards the right direction by the same amount, by the same number of units that we subtracted this time. Okay, so the red one is my translated graph, whereas the black one is just the parent quadratic function. In the same manner, we can understand the vertical translation. Let's assume that my original function is y equals fx. Vertical translation takes place when we add or subtract something to its output value. Means we don't manipulate the x value this time. We add or subtract something externally. So it's plus minus. We add or subtract something, let's say k. We again consider the similar kind of function. Suppose it's y equals x squared, which is my parent quadratic function. And now the translated function I'm going to assume is x squared, say plus 3. Just because I'm adding something externally means output is being changed. So the graph of the original parent function looks like this. Now if I added something here, I added 3 to this function, to this output value, my graph will get shifted towards the upward direction by the same amount, by the same units. So it's 3. It got shifted towards the upward direction by 3 units. Similarly, let's say I have the same function again, and I subtract something to its output value. Let's say it's x squared negative 3. And this time if I subtract it here, my graph will get shifted towards the downward direction by the same amount. So this is the graph of my original function, and just because I subtracted to its output value, it gets shifted towards the downward direction like this. So now horizontal and vertical translation can occur simultaneously. That's what happened in the vertex form. The horizontal as well as vertical translation occur together. So when the graph is shifted in the right direction, it means something is being subtracted. And when something is added to the output, it means it's getting shifted towards the upward direction. So if you notice the equation of this vertex form, it's y equals a times x negative h whole squared plus k. So what happened exactly? We used to have the function as y equals ax squared. When I translated it horizontally, means I changed its input, that is x negative h whole squared. Further, I performed the next translation by adding something to its output value, which is y equals a times. So this is my function now, and I'm going to add something externally. That means it's the vertical translation. So overall, this is my equation for the vertex form, where h and k can be considered as the vertex of the parabola. Just like 0, comma 0 used to be the um, vertex or the turning point of my original function, just because it got shifted in the right direction by h units and in the upper direction by y units, sorry, by k units. So it can be considered as h comma k. So h comma k is the vertex of the parabola in the vertex form. Also, we can get the axis of symmetry using this equation, x equals h. And leading coefficient rule is similar as the standard form. If the leading coefficient is positive, the graph opens upwards, but if it's negative, the graph opens in the downward direction. Let's have an example now. We need to graph this function. So first of all, we compare it with the vertex form, which is y equals a times x negative h whole squared plus k. So we can first of all compare the values of h and k. This is my 2 and this is 5. So as we compare the value of h, so negative h is compared with positive 2, means h is going to be negative 2. And if we compare k and 5, yes, k is equal to 5. So in this manner, we can consider the vertex of this quadratic function is h comma k, which is negative 2 comma 5. Let me write here. It's negative 2 comma 5. We can also get axis of symmetry now. Formula for axis of symmetry is x equals h. So we can easily figure it out. That is x equals h, and it is x equals negative 2. So x equals negative 2 is the axis of symmetry. So we can easily figure it out. That is x equals h, and it is x equals negative 2. So x equals negative 2 is the axis of symmetry. Also, the leading coefficient, as we compare the value of a, the a equals negative 1/4. It's a negative value. Just because it's a negative value, we can consider the graph to be opened in the downward direction. That is a kind of inverted U-shaped. We got a lot of data about the graph. Also, the leading coefficient Also, the leading coefficient is a, which is negative 1. We can also compare the value of a. A is the leading coefficient, and that's negative this time. It means the graph opens in the downward direction. We can still have few more points that will help us to plot the graph more easily. Let's draw a table. Let's draw a table, and there we can consider certain values of x, and then we'll get the corresponding values of y using the same function. Let's assume x as 0 or 2. So at x equals 0 and at x equals 2, we need to get the value of y. So the function is given as y equals negative 1 over 4 x plus 2 whole squared plus 5. Same function we need to use even here. Let's rewrite it. Okay, let us substitute the value of x as 0. So as we put x as 0, that's going to be 0 plus 2. And we simplify this. It's 4 plus 5. That's going to be positive 4. Similarly, we can get the value of, we can put the value of x as 2. That's going to be 4 fours or 16. So 16 and plus 5. We simplify this, and that's going to be positive 1. Okay, so the 2 points we get here, 0, 4 and 2, 1. We can consider them as ordered pair, and that will help us to plot the graph. Now we are all set. We can now open the graph sheet and plot our graph. So this is the y-axis, and this is my x-axis. And let us plot the points we've got. The first thing we need to plot is the axis of symmetry, which is x equals -2. Let us plot it. X equals -2 is plotted here. And then after we plot the vertex. Vertex we've got as -2, 5. Let us plot -2, positive 5. 1, 2, 3, 4, 5. Yeah, somewhere here. This is the vertex. Now we have a few more additional points. So we have 0, 4. So 0, 4 is somewhere here. Okay. Similarly, we have another point which is 2, 1. Let us plot 2, 1. So just because we already have an axis of symmetry, we can easily plot its symmetrical point in the other direction. So let us plot an additional point here, which is the image of this green point. Similarly, we can have the image of this blue point, which is at 4 unit distance from the axis of symmetry. Okay, so we have plotted all the points that we had. Now it's time to connect them with a smooth curve. So that's all about the vertex form of a quadratic function.